please welcome Marc and Gill, and of course, Brian Heater back to the stage.
Always a pleasure. Gill? All right. So this was alluded to in between, but the two of you have known each other for quite some time. Got a photo, if we could put that up right now. I asked Marc's team for a photo. This was, I guess, the oldest one that they could find, which surprised me because this is from your DARPA days. This actually isn't all that long ago.
2015, something like that, maybe 14.
I think maybe even before then, yes.
Yeah. So, Marc, do you recall the first time you met Gill?
Well, I remember talking to Gill when I think I was a professor, and you might have been, were you a professor? You were a postdoc?
I think at the beginning when I met you, I was a graduate student, actually. And I saw you for the first time, yeah.
And I had worked with a professor, remind me his name, who you'd studied with.
Oh, with Jerry Letfin, yes.
So Jerry Letfin was a real institution at MIT, and I'd done one experiment with him back when I was doing neurophysiology, which I had done when I first started grad school there. And so we talked about that.
And Marc, you effectively ended up inheriting the leg lab, is that right? Or sorry, excuse me, Gill?
Yeah, so Marc was an incredibly generous professor, and I had mentioned to him that I was going to tell him things that are going to make him turn red. But one of the wonderful things about MIT at the time, and about Marc in particular, is that I was this young kid, and both as a graduate student and then later as a junior professor, he just welcomed me. And so for a while, both of us were working in the leg lab at the same time. And Marc had done this extraordinary work on robots that run. And I decided, well, maybe I'll work on robots that walk. So that's sort of how we had intersected then. And then when you went off to form Boston Dynamics, you were very kind, and you just basically gave me the lab and all the stuff that was there.
What were the big problems you were trying to solve in those days?
Well, when we first got started, all robots that had legs were very slow-moving, crab-like things that would hug the ground and then, very tentatively take a step and hope that things didn't topple over and then move, like a spider or something, like a slow-moving spider. And I just took a look at that. I was interested in how animals worked. I looked at that and said, wow, this is about as far from right as you can get. And so, I went the other way and said, let's see if we can do something where the dynamics, the energy in the machine was part of the story, and springs and bouncing were part of the story. And my lab worked on that. So we did pogo stick robots.
Yeah.
And, it was kind of a leap of faith. Everything was going to be harder, but then everything got a lot better once you were willing to take on that. And I think that's the model for research. Sometimes you have to go up the hill before you can go into a sweet spot where things are going to work a lot better. And I think we're there even now.
So Marc goes off to form Boston Dynamics. Gill, you inherit the lab.
Yeah.
What kinds of problems were you working on, and how had it evolved since Marc's days?
So we worked on robots that could walk, and it turns out that walking, strangely, paradoxically, is actually a little harder in some cases than running. And you can tell this yourself if you're walking down a hill and the footing's not so good, maybe there's some leaves. It's often easier to just run down the hill than it is to walk slowly down the hill.
That's why our motto was you have to run before you can walk.
Absolutely, and Marc was right. So we had worked on walking robots for a while, and in particular on new kinds of actuators that were closer to what muscle is like. So they had springs on the inside. They were called series elastic, and trying to make progress on that sort of stuff. We also worked on the control, and this is, I think, what is leading to the kind of work both of us are doing now, which is, how do you get a machine to be as competent at physical tasks as an animal is, even something like a cat or a dog, or even lower animals like, mice. And it's remarkably hard. I think the two of us, we worked and we thought and we thought and we thought, and it's only recently that I think that we're starting to see ways that we can really achieve that.
Well, so you're very good at these segues. The two of you, again, the two of you have known each other for a long time, and I think what's really interesting about your respective careers is that you've kind of dovetailed in an interesting way. You're both running these research institutes that are effectively funded by automotive companies. Gill, you've been at TRI for some time. In a case like that, where the company is, again, supported by, or the research is supported by a company that makes cars, has to make money, is there a lot of pressure to productize?
So there actually is not, and I am not saying this, just to be nice, but I think one of the great things about companies that have existed for a long time is that this isn't the first time that they've done R&D. And certainly most of the R&D budget inside of Toyota is spent on figuring out how to make the next car, maybe the car 5 years from now. But there's this notion, and I'm sure that Hyundai shares this as well, that we're at the once-in-a-century time of transformation for the car industry. And battery electric vehicles, the new kinds of cars that are being made, are much simpler to make than the cars have been in the past. No engine, no transmission, etc. And so we're going to have to compete in a much fiercer way on cars, but also can we use the skills and the dreams and the hopes of the company to go beyond cars. And so TRI's job is actually think about what's next, what's going to be next after cars, as well as some kind of fancy stuff on cars.
And I would, if I could say for Hyundai, I think, in fact, I've heard Gill say that making a car is taking small bits of metal and banging them up and then welding them together or attaching them somehow.
Okay.
And that's a little on the primitive side. And now we have software, robotics, AI, all that stuff, and the car companies need to embrace that. And I think that the leadership at Hyundai, the chairman visited me last week. We're in close touch with him and the people who work for him, and they think that getting into the 22nd century is an important thing to do, and we're getting started on it now.
And in addition, just to build on that, there's actually this alignment that's happening between cars and robotics as well. I think actually Rod Brooks was the one a few years ago who said that modern cars, what are they? They're elder care robots. And I think that that's really true. You think about the amount of computers in them, the amount of software that's in them. And so actually TRI has different divisions inside of it, one of which actually works on very advanced things in cars that is completely overlapping in some of the software, some of the concepts that we're using in the robotic space.
Elder care is just a big focus for TRI in general, and I think a big motivating factor is the aging population in Japan. How is it essential to the work you do?
So we think about this problem of aging society, and it's actually kind of a worldwide thing. It's not just Japan, it's going to happen in the US as well as a result of the baby boom after World War II, but not quite as bad. But it's happening in many different parts of the world. And the truth is, and I'm sure this is true for all of you, growing old isn't fun. And particularly for our parents and our grandparents, we've all watched how difficult that can be. And so the question we ask ourselves is, can't we do better? Can't we improve quality of life? And of course, there's the physical part of it, that it's sort of hard to bend down and grab stuff as we did when we were younger. But we're also looking at the social side, the loss of purpose, the sort of feeling of what's the meaning? Why am I here? Do I still have something to give? We joke all the time that our goal is to build a time machine. What we really want to do is take 20 years off of people's lives. I watch Futurama, just like lots of other folks. I don't know how to build a time machine, but maybe the machines that we do build could have the capability to allow people who use them to feel that they can still do what they could do when they were younger. That's the goal.
Marc, you and I have spoken about this a few times, but you were leading Boston Dynamics for a long time. Sounds like you weren't entirely sure what was going to come next once Boston Dynamics really started productizing. What was your early pitch to Hyundai for this large amount of money that they gave you?
The pitch was very simple. It was that working on products was only going to take you so far. And you really, if you were going to solve the big problems in robotics, you had to have a longer timeline and build up a team. You want the kind of teamwork that you get at corporate lab, but you want the kind of futuristic thinking and not caring about legacy that you get at universities, and that you could have a lab that was a mixture of those two. And that was the concept for what we do at the AI Institute. And it was very short pitch, I think 8 pages, and they went for it.
You contrasted it with corporate R&D divisions, but how is the work that each of you do different than, obviously you both have university backgrounds. Gill was doing that for quite some time. In this kind of institute, what's the difference?
Between that and the university?
Yeah.
I think that, this isn't true of every university, but mostly it's professors working with a team of students. The students have some skills, but as soon as they really have skills, they disappear.
They're there to learn
They go
skills.
get a job.
Yeah.
And at a place like Boston Dynamics, and what I hope will be the situation at the AI Institute, you have teamwork where people have skills at all the various disciplines. They're brought to bear on a project. You can have a larger scale of activity. And this session is called hardware, but being able to work on real hardware development and have it mated with real software development and AI, it's really hard to do that in a university scale lab.
And I would also build on that at TRI. It's very much the same sort of thing. There's also a thing that I learned at DARPA that I think both of our labs share, which is this thing called Pasteur's Quadrant. And the idea there is that it's use-inspired fundamental research. And many people get confused by that because it's not on a single scale, but it's this two-dimensional idea. And we're always thinking about, if we're successful, how can this suddenly enable all kinds of new products? But we're not driven to solve a particular problem with a product the way that many of the other R&D efforts are. At the same time, we want fundamental understanding. So we're acting very much like academics, like scientists, asking why does this work, and how can this be a transformational change?
And I would go out on a limb and say that so I've been giving talks in which I say that we want to be the Bell Labs of AI and robotics, but we also want to have no products. Because as soon as you have products, you have customers, and then customers have things that they want, like 10 features that you didn't have. So if you have 100 customers, you have 1,000 features, and those features might not be in the direction of solving the more significant problems that really prevent robots from being what we dream about. As smart as people, as agile as people, or smarter and more agile.
One thing that really jumped out at me when you made the initial AI Institute announcement is that it's the AI Institute. You're a hardware guy. It's not the Robotics Institute. Obviously, some crossover, but why is that the main focus?
So first of all, we are equally focused on hardware and AI or cognitive intelligence. The name was a side thing.
AI was hot.
It really should be the AI and Robotics Institute. Robotics Institute's already taken, so there was just some politics. We are actually going to rebrand ourselves soon. Our official name is the Boston Dynamics AI Institute, which causes all kinds of problems because we're a totally separate company, except for that I'm involved in both. And so everybody's confused and thinks we're connected at the hip, which we're really not. So we're gonna work on that.
Okay. You haven't picked a name yet?
No.
Okay. But AI is something that you've really been focusing on recently.
Yeah. The whole idea is to make the robots physically able, like the Boston Dynamics robots are, but to make them smarter so you can interact with them. You don't need a fleet of programmers to program every skill, like Gill's group has been showing. And I guess you had a press release 2 days ago. And did you show stuff here?
We haven't yet.
Okay, you're gonna now.
You kind of showed my hand a little bit there, Marc. Sorry. Well, that's a good segue. If we could show the video right now. So as Marc alluded to, this news broke earlier this week. I visited you in your labs and wrote a piece about it. Gill, talk us through what we're looking at right now.
Sure. So this is actually some older video from last year, and what it's showing is things that we achieved in a very narrow slice of the robotics work that we do that's actually done by programming. And you can see some of the code in the background here, and that's a before shot. This is an after shot. This is the more recent work that we're doing. And as we discussed in the press release, and we're going to talk about even more, in this case, we have figured out how to do something which is to use modern generative AI techniques to enable human demonstration of both position and force to essentially teach a robot from just a handful of examples. The code is not changed at all between any of these examples. And what this is based on is something called diffusion policy. It's work that we did in collaboration with Columbia University and MIT. We've taught 60 different skills so far, and the goal is actually something that you see here called fleet learning, which is when one robot learns something, all robots learn the same thing, and that they can compose those skills together in a single whole. There's many, many steps that we're going to need until we get to robots that are as capable as people or as animals, but we think this is a very significant step that we've made and a bit of a breakthrough.
Can you draw a parallel for me between large language models and large behavioral models?
Yes. So there have been other groups that have been doing very good work where they take a large language model and essentially use the robot as an input-output device. So the sensors of the robot and maybe a little speech recognition is used to translate what the robot sees and what is said into a language command to a large language model that runs just like ChatGPT runs. It spits out something to do, and then the robot kind of in the output mode goes ahead and does that. That's not what we're doing. You can think about that like two things made it together like this, the robot and the LLM. What we're doing is actually putting things together where the diffusion policy, what we're using, is actually integral to how the robot itself learns each one of the skills and how the robot executes the skills. And I think that's what's so exciting about it. And I'm sure there's going to be lots of work from all over the world on this kind of way of doing things. So instead of using language, instead of using words, we're using both words and also input from human beings and also sensors and actuators from the robot itself. So we're changing it from large language model to large behavior model.
One of the things that you told me that was interesting is the contrast between this and what Boston Dynamics has been doing traditionally. Obviously, you've got a lot of robots out in the world. They're out there interacting with the environment. How distinct, Marc, is an approach like this from what you've done traditionally?
How what?
How distinct are the two approaches?
Traditionally, yeah, they're distinct. Traditionally, we program the robots by people creating control systems. Lately, those are MPC, or model predictive control systems. And boy, that stuff has really gotten sophisticated, including very recently. I kind of find it painful that people call that the traditional method compared to the learning method, but it's very powerful. I think it's going to continue to have a life and a role as things move forward. But that's different. But you still need a room full of very skilled and accomplished programmers who spend a lot of time making, the kind of things you've seen in the videos of Atlas running around the parkour course, or throwing the bag up to the guy on the higher level. If you watch YouTube, you've seen those things. This is really a different paradigm, a paradigm that we're hoping to work on or accomplish something too. We're only a year old, so we don't have anything to show like these guys. But the whole idea that you can tell a robot to watch someone do a task and then be able to figure out how to do it. Can we show that picture?
Yeah, let's pull up the first slide.
I think it's on deck there. The model here is, rather than have a room full of programmers, tell this robot, watch that guy. This is called watch, understand, do. Understand what you're seeing, and then do it yourself. And there's a lot of richness in that problem. What does understand mean? Segmenting the various tasks, having a concept of a sequence and what's trying to be accomplished, figuring out what skills to bring to bear if you already have some available, or learning new skills from watching the task being done. It's a very rich problem. And we have a team working on that and starting to make progress. The large language models play a role, but the tokens in a large language model, which are words, aren't grounded in the physicality of doing tasks like this, which involve joints and motions and energy and forces and compliance
So
and
to
things
break it
like
down,
that.
when you say open a door to a robot, it doesn't necessarily know what that is or how to execute it.
Right. It might not know that it might be able to figure out from a language model that it has to grab the handle and turn it. But what about the traction that your fingers need on the doorknob in order to turn it? And is it a push door or a pull door? And where do you have to stand? And if you're a quadruped walking through a door, it's not the same as being a human or a humanoid going through the door. So there's a lot to do to go from a simple description to doing it. On the other hand, if I asked either of you to do those tasks, you'd have absolutely no trouble,
Well, I might in my
instructions.
current state, but yeah, generally
Right.
that's true.
There is a part to this that's also, I think, very important to point out that is new. There have been successful research attempts before to get a robot to mimic what a person does. For instance, if you do a teleoperation like you see at the beginning of the movie that we had played, getting that to play back and having the robot duplicate what the person does, perhaps with a little bit of robustness if things aren't quite placed the right way, that has been done. The new thing, what's so exciting about this, is this idea of composition. So for instance, if any of you are asked to do a task that you've never done before, well, the fact that you've lived from being a little kid up until now actually provides you with tremendous numbers of skills of competence that you can compose together and blend together in a way to do the novel task. That has not been possible before, and so what's exciting about this is it's not just that we're learning from people, but we're learning in a way that things can compose. And if you think about large language models, that's what's so exciting about them as well, that they can compose from many examples in language from what they learn to come up with something that's a blend that makes sense. We're hoping that exactly the same thing's going to happen now with these behavioral models.
One of the themes along that line is we're interested in mobile manipulation and taking advantage of a robot that moves around. And if you guys could all do an experiment, which is to sit at the dinner table tonight and keep your shoulder stationary and see what you can reach on the dinner table. It's approximately nothing. Maybe the plate, but you probably can't reach your water. Whereas if you just have the mobility of doing this, you can reach everything that's in front of you, and of course if you can get up and move around. And if you're technical about the details of how an arm works, you can relieve singularities by having mobility. So there's a whole other world, and really that's the composition of mobility with arm or hand-based dexterity, which is just an example of what you're talking about.
Yeah, if we could advance through the slides.
One of the things we're trying to do, we're not actually building applications, but we're trying to keep in focus both industrial uses for what we're doing and consumer or home type uses. So this is another watch, understand, do situation where you watch someone cook something, you figure out what's going on, and you can do it. And we also have a project that's more focused, the next slide, on mobility. Very advanced dynamic mobility. I tried to sell this at DARPA about 10 years ago, the idea of putting wheels on the end of legs and throwing mass around, and they said it wasn't far enough out, to be honest.
That this is too realistic, what we're looking at right now.
That the idea of having wheels on legs was not aggressive enough in terms of pushing the boundaries, which I don't think is true, but that's what at one time was the reaction I got.
I have to ask, obviously you're the leg guy, you have been the leg guy. There's a big debate, legs versus wheels. What do you get from putting wheels on legs?
Oh, well, you get all the opportunity of being able to go fast if you have a prepared surface, but you can also go over anything. I'm not the leg guy anymore. That was before. Now I'm the everything guy.
Well, and I would point out that there's a lot of renewed interest in humanoid robots as well. I know that you're going to have some here from our good friends at Agility. It's incredibly neat and wonderful At the same time, I think that we have to always keep in mind that there's a human tendency to project a whole bunch of things on a robot based on how evocative it looks. And the reason is that we have this evolved thing in our brains where we recognize other people and it creates certain emotions inside of us. Even when we see an animal that moves in a certain way, there used to be folks who wrote in response to the YouTube videos that were at Boston Dynamics, all kinds of emotional things that they ascribed to the robot that was being pushed a little bit. And oh, that poor thing,
I'm going to correct you,
kinda,
the used to. That is very much still going
Still
on.
there.
yeah, so why does that occur? And it's because, we have this kind of ELIZA effect where we just identify with the machine. When making engineering decisions, what the form should be, there's a lot of uses for humanoid robots, but it's not a cure-all. That's only part of the answer. And the hardest answer is what's going on in the robot's brain and also in the network of all robots together that are helping each other to learn.
I want to add to that. I don't know how many of you remember the expression, if it walks like a duck and it talks like a duck and I don't remember what the next one is, then it is a duck. But in robots, that's just not true. It can have 2 legs and 2 arms like a human. It can climb stairs like that where it looks like a human. But it doesn't have the emotions of a human or the morality of a human or necessarily the intelligence or the language. And, robots are these constructions where you can decide what features and elements are going to be in there and then, work on those. And they're not put together the way humans are just because they might look like a human in some respects. And that's a real confusion to the public at large, I think.
It's interesting, as we were looking at the cooking slide, it occurred to me that that's not dissimilar, Gill, from what your team has been working on. And in that case, and in the case, I visited your labs a while ago, it is effectively a humanoid robot, or at least a robot with a face. Why is that important for a robot like that?
So there are elements of the built environment that we all have, and the robot has to have a form that somehow works in that environment. The humanoid form might be the one that you first think of, but it's not necessarily the only one. So for example, a while ago, we had a machine that was a robot arm that was hanging from a gantry on a ceiling as an example. So again, it's important not to get too enamored with the form. Both of us love the hardware side of things, and there's still work to be done there, and it's exciting and it's great, but there's also all this other work on the intelligence in the machine itself. And even more importantly, what's the purpose of the robot, even if you're not worried about products right now? Our view is that, like I told you, we want to effectively help people be younger. And so what that means is helping them, amplifying them, but not replacing them. Because if you replace a person, if you have a robot that cooks meals for you while you sit and do nothing, you're going to feel worse. You're going to feel that you have no purpose. On the other hand, a machine that helps you as you cook in order to help make meals for your kids and your grandkids and your friends, you feel younger because I can still do something meaningful.
So let's throw up the final slide. This has a lot of the images. Marc, when I visited your offices in Cambridge, if you walk into the lobby, these are all up for everyone to see. Why create renders like this, and what role does this play in the actual work that you do?
Well, we have a list of projects that are related to these pictures and others that aren't here. We're not working on all of them yet, but it's an idea for what to work on. To be honest, in these early days, I used to go around and only show videos of results, and that's the way I'd give a talk. Well, we don't have any results, so this was a way of kind of conveying the kinds of things we're hoping to accomplish. So, I just worked with an artist. These are not made by Dolly, which a lot of people ask me about. These were made by, me talking to an artist, and then he cooked something up, and I would tweak the instructions a little bit, and he'd make it a little different. And they're just meant to convey projects we want to work on. Watch, understand, do. One of them is called Inspect, Diagnose, Fix. Dynamic mobile manipulation. and a bunch of others.
Yeah. We've only got a few seconds, so I'm going to ask you both a really big question, and give me as short an answer as possible. How far out are we from general purpose robots?
I want to distinguish it from human level AI, because I don't think we need human level AI for general purpose robots. I think the answer is between 5 and 10 years from now. And the reason I say that is that it has to be true, because if you look at the aging society curves, that's when we're going to need them. It's going to take a while for them to spread and for the businesses that make them to grow. So our own timeline that we're using, which is set by those aging society curves, is 5 to 10 years from now.
You know, I generally agree. I think you could argue that even the Spot robot, you know, we have about 1,200 Spot robots out there. And if you look at all the different things people use them for, there's some argument that we're starting to embrace.
It has an SDK, which helps.
It has an SDK. It has a hardware roof rack, so you can attach whatever stuff, and there's, you know, there's connectors and things. And so people are adapting it for all kinds of stuff. Now, you know, the intelligence you need to make all that work is still a work in progress, but there's certainly a lot of generality to the things that can be used. On the other hand, I think the sense of your question is, when are they going to be more like people and instructable? And I think Gill's right. Maybe the outside of that, more like 10 years. I mean, it took Tesla 12 years to go from their first demo electric car to the Model S.
Yeah.
And you could argue that that was a pretty straight path with a pretty well-defined market, and we have a tougher challenge than that for robotics.
Great. We are all out of time. Gill, Marc, thank you so much.
Thank you so much.
Thank you.